In this video, we will be discussing the concept of vector addition in order to help you determine whether a molecule is polar or not by adding up the vectors that are representing the dipole moments of particular bonds. Let us first consider one-dimensional vector addition. This occurs when both of your vectors lie along the same line. So to add two vectors that lie along the same line, you can assign a particular direction as being positive and the other one as being negative. Then you add the two together. So in our first example, both vectors have the same magnitude and are pointed in the same direction. In this case, vector A is 5 units long, vector B is 5 units long. So to add them together, we would just take 5 plus 5 and align that in the same direction as the two vectors that we were working with. So the resulting vector is going to be the sum of the lengths of A and B, giving us a length of 10 units. We could also have vectors that are pointing in different directions. Let's say one vector is longer, 10 units long, and the other vector is shorter, 5 units, but pointed in the opposite direction. Because it's pointed in the opposite direction, we will change the sign on it to give it a negative and then add the two values together. So that would be 10 units to the right plus negative 5 units, this time going to the left. Or you could think about it as 10 minus 5. 10 minus 5, or 5 plus negative 5, results in a vector, our resulting vector, being 5 units to the right. We could also have two vectors that are pointing in opposite directions and are equal in magnitude. In this case, A is pointing to the left 5 units and B is pointing to the right 5 units. When we add the two together, they completely cancel each other out, resulting in a null vector, a vector of 0 length. If, in this case, we were looking at bond polarity, an example of this would be carbon dioxide, where you have the carbon in the center and the two oxygen atoms have dipole moments that are pointed in opposite directions. They will exactly cancel each other out, giving us a net dipole moment for the entire molecule of 0. Things become significantly more complicated when we are adding vectors in 2 or more dimensions. There are several methods for adding vectors that occupy 2 or more dimensions. One method to add the two vectors is to draw a parallelogram in which the two vectors form adjacent sides. So let's say we're adding vector A, which points up and to the right, and B, which points slightly down and to the right. To figure out the resulting vector from the addition of the two, you can draw a parallelogram with A representing one side and B representing another. This gives the resulting vector being along the diagonal of distance or length r. Another example has A pointing up and to the left and B pointing up and to the right. When we add the two vectors, we draw a parallelogram with A being one side, B being the other, and then the resulting vector goes along the diagonal. Another method for adding two vectors together, which is very similar to this one, is to take our vectors, draw one, and then start the second one where the first one ends. So let's say we were taking vector A that we have here, and we're going to add our vector B. So we would first draw our vector A, and then we would draw vector B starting at the end of vector A. The resulting vector starts where A started and ends where B ends. That would be your vector. So you can either use the idea of a parallelogram or starting the second vector where the first one ends. When you're adding 3 or more vectors together, it's best to initially add 2 of them together to get a resulting vector. So we could add A and B together to get our resulting vector, and then add that resulting vector with your third vector, giving you this new resulting vector. So if we wanted to take A plus B plus C, a good method is to first add A and B together, getting R, this R here, and then take that R value, that R vector, and add to that the C vector. So essentially, make your first parallelogram, collect the vector, then make another parallelogram using the resulting vector and the third vector that you wanted to add together. In some instances, when we're adding three vectors together, another example that we can have is something that is highly symmetric, as is the case with example labeled 7 here. This would be something like a trigonal planar geometry, where A, B, and C are pointing along the faces of a triangle. So B is the same length as C, which is the same length as A, and they were all symmetric in the directions that they're pointing. So we add A with B together, we get the resulting vector R. The resulting vector itself cancels out the C vector when we add the two together. So for things that are very symmetric, as is the case with many of our molecular geometries, particularly those where the molecular geometry and the electronic geometry are the same, examples being trigonal planar, tetrahedral, some forms of trigonal bipyramidal, and octahedral. If all the groups coming off of the central atom are the same, then a lot of those molecules are going to be nonpolar because through the symmetry and the addition of all those vectors, they end up canceling each other out, as is seen with this example 7. So for highly symmetric molecules, a lot of times the vectors are going to cancel each other out. Finally, let's look at how all this talk of polarity and vectors gives us something that we can use. Polar molecules are attracted to other polar molecules. Because water is a polar molecule, other polar molecules will be able to dissolve in water, as well as ionic compounds. Because when ionic compounds dissolve, they break apart into their plus ions and minus ions, those can be considered point charges. So the charge, or the dipole on our water molecules, which has a negative end where the oxygen is, a positive end where the hydrogens are, those dipoles are going to interact with things like ionic compounds. We also can have molecules that have both components in them. Some molecules will have both polar and nonpolar parts. An example would be a soap molecule. Soap molecules have both a polar end and a nonpolar end. We could think of the polar end as labeling it with a circle. So this would be our polar phosphate group. And then you would have a nonpolar group, which would be the lipid. The way that soap works is if you have some grease or something that you're trying to get off of your hands or some material, the nonpolar group will interact with the nonpolar grease. And you'll end up forming your dirt on the center. So if this is your dirt, you then have all your nonpolar groups from your soap pointing towards the nonpolar dirt, and then your polar end of soap pointing outward. And that polar group on the end is going to interact with your water. That is what takes the dirt and the grime and makes it soluble in water. It is the nonpolar end of the soap molecule that is interacting with your dirt and the polar end of the soap molecule that is interacting with the water. This enables the dirt to become soluble in water and to be able to be removed from whatever you're trying to clean.